let A comma B comma C be subset of R. Let F be defined from A to B. Let G be defined from B to C. Let the range of F be subset of B. Let Y is equal to F of X and Z is equal to G of Y, which is G of F of X. One. Let F be continuous at X is equal to C. 2. Let G be continuous at Y is equal to G of C. Then 3. G of X continuous at X is equal to C, right? So this is composition of function and we are trying to check continuity of composition. बरोबर मी कर 12वीची मुलं काय जॉईन करायला बघतायत वृद्धी साहिल शार्दूल दाते ऋषिकेश वाळवेकर okay so try to prove this theorem. Okay, let us draw a picture of what we want to say. There are 3 sets, basically A, B and C. From A to B, function f is operating. From B to C, function g is operating. The variable here is x, this is y, this is z. Okay, so that is what is the setup. And now when we want composition g of f of x, that means who all are present here, they will have their image in B and there will be a range of images of all xi's in set A. And then if we operate this g function is defined from B to C. There could be yet another element here who is getting converted under G and becoming somebody here. That is fine. But what we are interested in our composition is a g function. What happens to this g function and with respect to all these images? What happens? And then it becomes a new set, and this is what is Z we are interested in. And therefore, all these people here, Z will be G of f of x. All these guys here are x's. They are x. These are z's. Okay. So this is what we are interested in. Okay. There could be some additional people sitting here. That is fine. There could be few more who are part of set B and under G. They are being projected in C. That is fine. But we are not interested in the remaining. We are interested in the z's and how these z's are created using g of f of x. That is what is a matters to us. Okay, this is what is composition of function. Now therefore if we want to prove that GOF of x is continuous, might as well it should satisfy definition of continuity. Yes or no? So now you think about how do you satisfy the definition of continuity for GOF. What is given? F is continuous, G is continuous. These are the two functions. Independently, they are continuous. Then GOF is supposed to be continuous. This theorem, we will, whatever composition that we are doing in everyday life, we will get permission to state about continuity of composition. Give you few more minutes. Proof. Let epsilon greater than 0 be given. That is, your epsilon is given for z. Z should be in the epsilon limits. That is what is given to you. So the simplest statement that we can make is for G, 2 says G is continuous, therefore 2 implies there exists delta 1 greater than 0 such that for every x belonging to not deleted delta 1 neighborhood of C intersection B. No, for every x, sorry. For every coordinate y. We have f of x, g of x, g of x, g of y.
So it should be delta 1 neighborhood of f of c, right?
Yes. Everywhere mistake. Lack of concentration. Intersection B, we have g of y minus g of y minus g of f of c absolute value is less than epsilon. That is statement number 4. Is it correct? Now let us check. For given epsilon, let epsilon be given. There exists delta 1 such that for every y, which is the independent variable in B belonging to delta 1 neighborhood of f of c intersection B, we have g of y minus g of f of c is less than. G of y is g of f of x. Okay, so let us write down. What do we mean by this? What do we mean by this statement? y belongs to, this means y minus f of c is less than delta 1. I mean, writing it this way or this way, it is same for every y such that y minus f of c is less than delta 1. We have this. Okay, so I am just writing the meaning of for every y belonging to delta 1 neighborhood of f of c intersection b. Instead of that, I am writing this. Fair enough. Now, y is here and this f of c, that is y, f of c is y, and how much f of c can move here and there? f of c, suppose this is f of c, then f of c can move here and there as far as delta 1. So epsilon for f is going to be delta 1. That is the key in this proof. Just try to understand. This is saying that if you want to remain in the epsilon neighborhood of z, you should be in the delta 1 neighborhood of y. Now, if we want to go back and look at f, that means if we want to be in delta 1 neighborhood of y, we need to be delta 2 neighborhood of x. Do you understand this? Here I cannot say epsilon because epsilon is here. Output is epsilon. And it is composition. So this epsilon will say that you have some delta 1 for y. And now if our composition, the cascading need to be done correctly, then epsilon for f is delta 1. Understand this, okay? So therefore, my first statement, 1 will imply there exists delta 2 greater than 0, such that for every x belonging to delta 2 neighborhood of C intersection A, we have f of x minus f of C is less than delta 1. This is 4. Okay, what is f of x? F of x is y. F of c, delta 1, delta 1. So now do you realize that there is a series which is happening? For there exists delta 2 greater than 0 such that for every x delta 2 neighborhood of C intersection A, we have f of x minus f of c less than delta 1. But f of x minus f of c less than delta 1, for every such y, we have g of f of x minus g of f of c less than epsilon. So 4 and 5 will imply 4 and 5 will imply there exists delta 2 greater than 0 such that for every x belonging to delta 2 neighborhood of C intersection A, we have absolute value of g of f of x minus g of f of c is less than epsilon. This A is equal to B is equal to C, therefore A is equal to C. It is similar to this. It is not exact, but it is similar to this. This implies this because of statement number 1. This implies this because of statement number 2. Therefore, statement number 5 and 4, 5 followed by 4 this, implies this. That is what I have written. And now what do we mean by this? This is GOF of X minus GOF of C is less than epsilon, and hence by definition GOF is continuous at X is equal to C. It is simple, but I mean we need to get it done through epsilon delta. Right down. So if I am asking you this question, limit sine of 3x plus 5 x tends to minus 3 by 2, the answer is sine of half. And I mean, who gave you the permission to do this? You have proved sine x limit x tends to c is equal to sine c. You have proved a limit 3x plus 5 as x tends to minus 3 by 2 is equal to half. You have proved this. We have proved this, right? So now this theorem which we have proved just now is giving us this permission of writing this answer directly. So limit f of x as x tends to c is equal to f of c. Suppose we write it like this. Suppose this is true. When is this true? When f is बोला बोला अरे बोला माइक चालू ठेवा आणि बोला पटापट.
Continuous
is continuous.
F of x
at C.
tends to c is equal to f of c. Suppose I write this. When can I write this? When f is continuous. बरोबर आहे? Yes or no? And then therefore what am I actually trying to do here is limit x tends to c f of x is equal to f of limit x tends to c of x is equal to f of c. This is the operation indirectly I am doing when I am writing this statement. Yes or no? Indirectly I am flipping calculus and function, limit and function. This here it was function followed by limit. No, sorry, limit. Limit followed by function here, and here it is function followed by limit. So I am flipping the two operations. Am I allowed to do that every time? No. When will I be able to do it? Is sin x continuous? Yes. Is 3x plus 5 continuous? Yes. Therefore, composition of continuity of composition is available. Yes. I need not have to keep thinking. Just put x back over here and write the answer. But in mind, or not in mind, but indirectly, we are following the rule of composition of function and continuity. We are flipping. So there could be a case where you will fail to do this if the function is not continuous and if you are not aware of this fact. By and large, majority of the time you will be able to do this successfully, but a function can be designed in such a way that you will fail if you flip limit with function, and that can be designed if the function is not continuous. So that is very important point which I am trying to make right now. unless and until you have continuity of the function in mind, you should not evaluate those limits blindly. That is the purpose. Make a note of it. Okay, let us create few new definitions. Let A be subset of R. Let U belong to R. U is said to be upper bound of A if and only if. Okay, complete this statement. That is what is definition. Write down the remaining part of the definition. Similarly, let A be subset of R. Let L belong to R. L is said to be lower bound. O lower bound. If and only if complete this statement also. If and only if for every x belonging to A, x is less than or equal to U. For every x belonging to A, x is greater than or equal to N. Example 2, 3. Is 3 an upper bound of set A? Is 3 an upper bound of set A? Yes. A 2, 3. Is 3 an upper bound of set A?
Yes, sir.
What happened to my mouse? Right? Okay, so both cases, yes. Is 100 an upper bound of set A? Yes. Of set B? Yes. And so on. Next definition. Let A be subset of R. A is said to be bounded above if and only if voila. What should I write after this? Let A be subset of R. A is said to be bounded below if and only if. Okay, tell me, what should I write here? A is said to be bounded above if and only if there exists U belonging to R such that U is an upper bound of A. If and only if there exists L belonging to R such that L is a lower bound of A. Systematic. Bounded above, bounded below.
Sir, you shouldn't be infinity condition येईल का?
Huh?
सर यू किंवा एल स्टुडंट बी इन्फिनिटी ही पण येईल ना कंडिशन.
नाही, u is a real number, l is a real number. Infinity plus or minus is not a real number. It is symbol. It is a symbol that we use for writing. The meaning of that is you give me a number, I give you a bigger number than that. That is plus infinity. That is the concept. It is not a real number. So we should not use this sign for representing real number anywhere in our writing. This is not a real number. When we say x tends to infinity, plus infinity, we should always use infinity either with plus sign or minus sign. Without any sign means plus is true for real numbers, but infinity is not real number. When we say x tends to plus infinity, it does not mean that it achieves some value here, real number. It means x is becoming very large. Okay, therefore these guys u and l must be real numbers. That means they are finite real numbers. How big they are, but they are finite. Now, next definition, let A be subset of R. A is said to be bounded. If and only. If and only if A is bounded above and below. Simple. Look at the elegance of these definitions. First, we define only upper bound. Similarly, only lower bound. Then we defined set which is bounded above using U. Set which is bounded below using N. Now using both these two definitions, bounded above and bounded below, we said set A is supposed to be bounded. That is what. And let A be subset of R. A is said to be not bounded above. If and only if, complete this, and A is said to be not bounded below. If and only if. If we complete these two statements, the ambiguity or the unknown statement that we had written in yesterday's definition, when we wanted x to tend to in plus infinity or minus infinity, that ambiguity is removed by these two definitions. So how do we write? How do we complete this now? A is said to be not bounded above if and only if. Complete kara. This is very simple. For every u, suppose you say that there is upper bound, there is an upper bound u. So whatever upper bound you want to give it to me belonging to R. It need not be the member of set A. You give me any real number which you think is upper bound. For every u belonging to R, I will give you there exists X, a member of set A. I will give you X which is a member of set A such that X is greater than u. That means it is not bounded up. For every L belonging to R, there exists X belonging to A such that X is less than L, not bounded below. समझते? Very good. Okay, next. Let A be subset of R. Capital M belonging to R is said to be the least upper bound of A if and only if. Let A be subset of R N belonging to R is said to be the greatest lower bound of A if and only if. Okay, now see, having written so many definitions, you should precisely write what is required now. Take your time, think about it, create your notation. If and only if 1 M is an upper bound and 2 for every U belonging to R, for every U belonging to R which is an upper bound, जरा हे मला खाली खेचायला लागणार आहे. For every U belonging to R which is an upper bound of A m is less than or equal to u. Then we will call m as least upper bound. M must be an upper bound and it should be least. Like LCM. LCM should be a common a common multiple and should be least. GCD. GCD must be a common divisor and must be the greatest. 1. N must be, N is a lower bound. And second, for every L belonging to R, which is a lower bound, N is L is less than or equal to N. So this is LUB definition, LUB, and this is GLB definition. Now these abbreviations will be used many times in our discussion.
Sir,
Hmm.
sir, we can also say that M is an upper bound.
13th property of real numbers. Before we write 13th property of real numbers, let us revisit what are the 12 properties of real numbers that we have already assumed. 1, A1, 2, A2, 3, A3, 4, A4, 5, M1, 6, M2, 7, M3, 8, M4, 9th, D, distributed, 10th, O1, order property number 1, 11, order property number 2, and 12th, order property number 3. So up to this point, we could develop only 0 and 1 in real numbers. The moment we assign order properties, we could develop all real numbers, right? And now we are at the point where we wish to develop still, I mean, we are not sure about irrational numbers. We are saying that we will capture them between two rationals. Okay, we are saying that y is equal to x square is continuous. We know it is 1, 1, 1 comma 1 at 1. We know it is 2 comma 4 at 2. But do you really know whether all these points are well behaved between 1 and 2? Whether all these points give you continuity between 1 and 2? You really do not know, and that is where we require calculus to figure out, yes, is there any real number whose square root, whose square is 3? Is there a real number a whose square is 3? Yes, a is equal to root 3. So does root 3 exist? Is it a part of this graph, and will it give you exact value 3 at some point, and whether it is exist? Presently what we are doing is we are just trying to catch this root 3 between two rational numbers, and we say that yes, eventually in limiting case we will be able to successfully catch this root 3 between two rationals, and if we keep on doing this process, we will get a real number a whose square is 3. That is what approach we have been taking so far. But now if we really want to legalize this approach, do not have any choice but to assume one more axiom of real numbers, which is what we call 13th property, and the English version of that is for every non-empty subset of real numbers which is bounded above has least upper bound. English version of that is every non-empty subset of real numbers which is bounded above has least upper bound. Nobody can question this statement. This is LUB axiom. Can we question the correctness of this statement? No, because it is axiom, assumed to be true. Is it easy to understand? Yes, of course. It is easy to understand. Primitive, very easy. And therefore, this is the last axiom that we would like to assume in real numbers, and everything else can be proved after this. Okay, so let me write down the mathematical version of this. Let A be subset of R. Let A be not empty. Let A be bounded above. अरे व्हाट्सएप कौन साइलेंट होता है? Let A be bounded above, then A has least upper bound. This is 13th property, LUB axiom. Now, question will be, will there be yet another axiom for greatest lower bound? Not required. No more axioms, because if we assume this, we can do the work and prove that greatest lower bound is the greatest element in the bounded below set. Something like that. May be part of that set, may not be part of that set, but it is the greatest element. Okay. So now this is important, non-emptiness of the set, because if I have a set which is A which is empty, what is the upper bound of this set? Is 5 an upper bound? Is 5 an upper bound of this set? Empty set? I mean, we have to accept and say yes, because how can I challenge and say no? Ambiguity, always ambiguity. So therefore we are not getting into this business, and we are making it clear that it has to be non-empty set. Then only LUB axiom is applicable. If it is empty set, it doesn't make any sense. If you have nothing to compare, what are you trying to compare? Okay? So if this axiom is available, I give you a theorem now which you should try and prove, called gap lemma. let A be subset of R, let A be non-empty, let A be bounded above, let M be LUB of A, then for every epsilon greater than 0, there exists X belonging to A such that M minus epsilon is less than X is less than or equal to M. What does this mean? This means to the left of GLB, to the left of LUB, you don't have gap. That is what this gap means. To the left of LUB, you don't have gap. I give you few minutes for doing this on your own, then we will write down the proof together. But it is important to understand what you are trying to prove. Okay, so what we are supposed to prove is there are no gaps if you have for every epsilon. Doesn't matter what value of epsilon you take, for every epsilon greater than 0, there exists X belonging to A such that M minus epsilon is less than X is less than equal to M. Okay, so how will the proof of this go? Of course, it is going to be contradiction. So, if possible, let open interval M minus epsilon to closed interval M is empty set. And M is LUB of A.
So that set intersection A will be empty, right?
Yes. Okay, shall I write it again? If possible, let M minus epsilon comma M closed intersection A is empty. Statement number 1. As M is LUB of A, this implies for every X belonging to A, X is less than or equal to M. Statement number 2. 1 and 2 imply for every X belonging to A, X is less than or equal to M minus epsilon. Correct? This implies M minus epsilon is an upper bound of A. By definition. And epsilon is greater than 0. that means m minus epsilon is less than m. Contradiction to definition of LUB. Therefore, this implies there exists X belonging to A such that m minus epsilon is less than X is less than equal to. Okay, so now just to confirm that you have understood this set or this theorem, suppose I have a set of natural numbers 1, 2, 3, 4, 5, 6, 7, 8. 8 natural numbers. Can you tell me what is LUB of this set? Suppose set A is 8 natural numbers. What is LUB of this set? What is LUB of this set? Eight. Correct? अरे हो का नहीं? आत ना सगळे. What is
हो सर.
this set? 8. Okay. Is gap lemma applicable here? Is it true here? Gap lemma working here?
No, sir.
Yes or no? Yes, it is working. Suppose you take epsilon is equal to 0.5. So what is m minus epsilon? That is 7.5. Is there a member of set A between 7.5 and 8? Yes, that is why this equality is important. This equality is important because now gap lemma is true because of 8. If epsilon is 2, then okay, 6 is less than equal to 8 and there is 7 in between. Some other value other than 8 and 8 is also there. Do you understand? If it is a discrete or isolated point set A is consisting of isolated points. Say for example, let me take another example. B, set B is 2, 3 union 4. What is LUB of this set? What is LUB of this set? 4. Least upper bound. Is it part of the set? Yes. So is gap lemma working here? Yes. Even if there is a gap between 3 to 4, still gap lemma is working because gap lemma says elements of A. And equality over here, that means if your LUB is a part of that, then of course it is present. Now, if you don't want your LUB to be part of your set A, so let us take that example. Suppose set C is 2, 3. What is LUB of 2, 3? 3. So now we opt a set C such that LUB is not part of that set. Is gap lemma still working here? Yes, it is working. Therefore, this is very important theorem. That is what is actually giving us idea about density of those points. To the left of LUB. Left of LUB is always crowded. Left of LUB is never empty. You don't have voids to the left of LUB. That is what this theorem all about, and these different examples will help you imagine this particular theorem very well. Proof is very simple. It is contradiction to definition of LUB. If you happen to have somebody which is an upper bound and smaller than LUB, then that fellow must have been LUB. Why is it capital M LU? M minus epsilon must have been LUB. That is what is a proof on this. Let me pause it. Set of real numbers is always a difficult set to handle because we are seeing that we just do not have next number or previous number, or what is, say, suppose your interval is 1 comma 2 open interval, then what is the first element of that set? What is the smallest element of that set? Open interval 1 comma 2, what is the smallest element of that set? It is difficult to give answers, and therefore it is difficult to deal with sets which are of real numbers. Okay, and now eventually we want to prove few things for real numbers, but then it is sometimes convenient to deal with the numbers which are not real numbers, but say for example natural numbers. Natural numbers, set of natural numbers, we are aware that there is a smallest element in that set, which is 1. To the left of 1 there is nobody, and the set starts from 1. Okay, so it is relatively easy to control the set. Therefore, now we are going to consider our domain as a set of natural numbers, and codomain always can be considered as set of real numbers. Does not have any problem. Okay, so if x is equal to 1, if x is equal to 1, y is equal to 2. If x is equal to 2, y is equal to 5. If x is equal to 3, y is equal to 8. If x is equal to 4, y is equal to 11, and so on. Suppose I am considering a mapping like this. This is 3. Suppose I am considering a mapping like this. I can always write it in without using x1, y, x2 or y, etc. I can always write it like this. A1 is equal to 2. A2 is equal to 5. A3 is equal to 8. A4 is equal to 11, and so on. And we are aware of this. This is called sequence. And in this case, it is arithmetic sequence, arithmetic progression. Okay. So sequence is a function from natural numbers to real numbers. That is what we want to bring it to your notice now. Sequence is a function from natural numbers to real numbers, and therefore a1, a2, an, consider this as a sequence. We write this as sequence. Actually, this is a function. What is the value of the function? An is the value of function when x is equal to n. So this is real valued sequence, which is a function from domain natural number to codomain real numbers. Okay, and therefore it is easy for us to control the domain points because they start from 1 and they are well behaved. We need not have to worry about all the points in the domain because it is a set of natural numbers, and our study or development of next theory becomes easy when we consider the domain as natural. So now we will consider the sequences. Is sequence a function? Are we deviating from our the aim? No, we are not deviating. Now it is difficult to deal with real number set, and therefore we are dealing with sequence. And eventually, if something is true for x is equal to 2, if something is true for x is equal to 3, will it be true for all points between 2 and 3 as far as real numbers are concerned? We will do that there. बघा लक्षात काय येते का तुमच्या? It is easy to prove it for 2, it is easy to prove it for 3, but it is little difficult to prove it for any real number between 2 and 3. So we will take approach saying that okay, we will prove it for 2, we will prove it for 3, and we will try to eventually prove it for every point being rational or irrational between 2 and 3. Therefore, we begin our study with sequences, and now therefore I need to create few definitions for sequences. Definition. Let an be real valued sequence. We say that an is convergent if and only if there exists L belonging to R such that limit n tends to plus infinity, an is equal to L. Now understand this definition well. Example. Suppose we consider a sequence 1/2 raised to n. So if n is equal to 1, an is equal to this. A1 is equal to half. A2 is equal to 1. A3 is equal to 1. A100 will be equal to 1 upon 2 raised to 100. Dot dot. Is this a sequence? Yes. And now if I take this value n, an is equal to 1 upon 2 raised to n. Suppose I take this value n to plus infinity, because natural number set is a infinite set. I can always take the values to the very big numbers, and hence this sequence is going to go to 0. Correct? So limit half raised to n as n tends to plus infinity is equal to 0. Hence convergent. It converges to 0. L is equal to 0. समझते हैं? You can have several examples like this, and it need not be convergent to 0. It may be convergent to some other value. Like that. So that is what is the meaning of convergent. the eventual values are going to go towards that number, and it is a real number. Do you understand this definition? Now, as far as this definition was concerned, we are using the definition of limit exactly same way, but now the function is for discrete values of n. It is almost, domain is isolated point, set of isolated points. It is, domain is not the continuous set. Domain is set of isolated point, but the same old definition will work here as far as we have just changed the domain from real numbers or interval of real numbers to discrete point set, which is natural number. Okay. Now I want you to create a definition. An is a real valued sequence %50. We say that An is increasing if and only if, simple. When will we say that An is an increasing sequence? If and only if An plus 1 is greater than or equal to n. No, I mean, what we will do is we say that An is non-decreasing sequence. Okay, if we are writing increasing definition, let us continue with that and say that it is an increasing sequence provided An plus 1 is greater than An for every n झालं एवढंच ना, n plus 1 is greater than n for every n belonging to natural number. Yes or no? That is what we will call increasing sequence. Maybe when we want to say that An is non-decreasing, if and only if An plus 1 is greater than or equal to n. It definitely is not decreasing. It can continue to remain same or it has to improve, increase for every n belonging to natural numbers. Okay, so now I am going to give you a thought for you. You just keep on thinking and then we will try to arrive at conclusion. Now, I have an increasing sequence and if I say that it is bounded above, an increasing sequence and is bounded above, what will happen eventually? it is an increasing sequence. N tends to infinity. And I am saying that it is bounded. And it is bounded above. Then what will happen? That is what is the thought